Welcome to the video lecture on linear programming. Linear programming is a modeling technique used to determine the optimal allocation of resources. It was developed during World War II to allocate troops and materials in different areas of Europe. Linear programming can be applied to very complex problems involving thousands of variables and thousands of equations. Airline schedules, telephone connections, and the trucking industry are just a few examples of industries making use of linear programming today. We're going to look at some simple examples where we can use a graphical approach by graphing a system of linear inequalities. This can be done as long as the situation can be described with only two variables. In more complex examples, you would have to use matrices and matrix operations to determine the optimal solution. So our first example has a retired couple who has up to $25,000 to invest. As their financial advisor, you recommend that they place at least $15,000 in treasury bills yielding 6% and at most $5,000 in corporate bonds yielding 9%. How much money should be placed in each investment so that income is maximized? So it's got a lot of stuff going on in this problem, but there's a couple of key words that you want to think about. The first thing that you want to look for is either the word maximum or minimum. And in this problem, we want to maximize what? We want to maximize how much money should be placed in each investment so that income is maximized. So what we want to maximize is income. This is called your objective. Whatever it is that you want to maximize or minimize, that is your objective. And that's the first thing you want to come up with, is some sort of formula that represents the quantity that you're trying to maximize or minimize. We want to maximize income. So let's see if we can come up with a formula for what this income would be. And what it is dependent on is how much we invest in treasury bills and how much we invest in corporate bonds. So let's let X be the amount invested in the treasury bills, and let's let Y be the amount invested in corporate bonds. So if the treasury bills yield 6%, and you're investing X amount of dollars, then the income that you would earn, or the interest that you would earn from just the treasury bills, would be the interest rate, written as a decimal, times the amount invested. So that would be 0.06 times X. To figure out the interest or income earned from just the corporate bonds, you would take its interest rate, which is this 9% or 0.09, times how much you invested in those bonds, which is our Y. So that would be 0.09y. And the two together give you your total income. So that's how we come up with our income formula. And notice that it's dependent on two variables, X and Y. So this is called your objective. It's whatever you want to maximize or minimize. And what we want to do next is come up with the stuff that we call constraints. These are kind of like your restrictions on what has to be maintained in this problem. So what are a couple of things that we know? Well, the very first sentence tells us that the couple has up to $25,000 to invest. And remember that X and Y represent the total amount of money that you have to invest in these two different types of bills and bonds. So if we invest X in bills and Y in bonds, that total of X plus Y can't exceed $25,000. So that's one equation that we can write down. X plus Y, and it's not actually going to be an equation, it's going to be an inequality because we have up to $25,000 to invest, so we can't exceed that. So our X plus our Y needs to be less than or equal to $25,000. Okay? Now, to make our lives easier, 25,000 is a pretty large number. So a lot of times what we'll do is we'll take away these zeros, and we'll just remember that our units here are going to be in thousands, since we will be graphing these, and it's going to get pretty yucky to have to graph 25,000, but it's not quite so bad to graph just 25. So I'm going to let my units represent thousands of dollars. Okay? So that's one constraint from this first equation. What else do we know? Well, the financial advisor, you recommend that they place at least $15,000 in the treasury bills. So how much money should we invest in the treasury bills? At least $15,000, and X is the amount of money that we're calling our investment in the treasury bills. So that means we want our X to be at least $15,000, and as an inequality, that means this needs to be greater than or equal to 15,000. And again, we're going to strip away those zeros by taking them away and maintaining the same units throughout so that we have smaller numbers to deal with. So we want our X to be at least 15. What about for our corporate bonds? We want our corporate bonds to be at most $5,000. So our corporate bonds is our Y, and we want that investment Y to be at most $5,000. At most would mean less than or equal to $5,000. And we're just going to take away those 3 zeros on the end. Now that would seem like it's it, but we do have 2 other implied constraints here. And those are the fact that however much we invest in X for these treasury bills, you definitely want that to be a positive amount of money. So greater than or equal to 0. And likewise for Y, however much you invest in your corporate bonds needs to be either 0 or a positive amount. You don't want to invest negative amounts of money. So this is what we have for our constraints. Now here's the process that we're going to go through to figure this out. The first thing we're going to do is we're going to need to draw a graph that shows all of these constraints. So we're going to graph all of our constraints at once. So let's do that over here. And what we want to do is shade in the region where all of these constraints overlap. So if I look at X plus Y less than or equal to 25, think about how you would graph that. That has an X-intercept if I let Y be 0 at 25. And it has a Y-intercept if I let X be 0 at 25. And it's a equal bar, so this is a solid line here. So that's the line itself. And now what about which part of this would we shade? Well, if X was 0 and Y was 0, in other words, if I looked at the test point of the origin, 0 is less than or equal to 25, so that would be true. So we would want to shade going down. Now before I do that, let me go ahead and look at some of the other constraints here as well so that my graph here doesn't get too colored in and too confusing. So we'll do the shading in a moment, but we just want to kind of remember that this is going to be shaded downwards. Okay, let's take a look at the next constraint. The next constraint was that X needs to be greater than or equal to 15. So here's 15 somewhere over here. X equals to 15 is a vertical line, and greater than or equal would be to the right. So we would want to shade to the right. So far the overlap of these 2 regions would be this V section in the middle. Okay, let's look at the next constraint, Y less than or equal to 5. So 5 is somewhere down here on the Y-axis, and Y equals to 5 is a horizontal line right here. Y less than or equal to 5 would be shading down. So now we're below this horizontal line and going down. And then finally, X greater than or equal to 0, that's just the Y-axis, and greater than or equal to 0 would mean shading to the right. So that's still in this same region over here. And then Y equal to 0 would be the X-axis, and greater than or equal to that would be shading up. So where do all of these overlap? Well, they have to be between these 2 parallel lines, to the right of this vertical line and to the left of this diagonal line. So we're talking about this region right here, this little shape right here. Now, we're not going to go into the proof of why this is, but it turns out that all the feasible places, what we call the feasible points, that would give me this maximum income, they turn out to occur inside of this region. And what we find out is that the solution for where this income is going to be maximum can only occur at what we call the corner points. So in here, in the shaded region, are what we call all the feasible points, all the possible solutions, but the ones that are going to give us our maximum, so the solutions that will give the maximum income, can only occur at the corner points, which is kind of nice because that means we have fewer places to look at. So what are the corner points of this shaded region? We have this one here, this one here, this one here, and this one here, and we need to find out what their coordinates are. So let's call this A, B, C, and D. So corner point A, what are its coordinates? Well, it's at the intersection of this vertical line x equals 15 and the horizontal line y equals to 5. So that means x is 15 and y is 5. Let's look at corner point B. Corner point B is down here. It's still at x equals 15, but its y coordinate is 0. Let's look at corner point C. C is at a height of 5, I know that much, but I don't necessarily know exactly what x it is. It's somewhere between 15 and 25. But what line is it coming from? It's the intersection of this line y equals 5 and this equation right here, this inequality right here. So to figure out what this x is, we need to find the intersection of y equaling 5 and this curve right here. So if x plus y is equal to 25, and we know that y is supposed to be 5, we can just substitute it in and solve for x. So that forces the x to be 20 if it's going to lie on this line. So that corner point C has to be 20, 5. And then finally, corner point D is right on that x-axis. The x value is that 25 because that was the x-intercept of this line, and the y value is 0 because we're on the x-axis. So here are my 4 corner points. Now how do I figure out which is the one that's actually the solution? These are just the possible solutions. These aren't necessarily all the solutions. So what you have to do to figure out which one is the actual solution is go to your actual objective function that we're trying to maximize, and we're going to plug each of these in to this income formula. And whichever one comes up with the biggest I, that's going to be our solution. So for example, if I take x is 15 and plug that in right here, and y is 5 and plug that in right here, we would get 0.06 times 15 plus 0.09 times 5, and you're going to have to trust me that on your calculator that gives you as a solution 1.35. You can plug that in to double check. Now let's do it for corner point B. So this is going to be 0.06 times 15 plus 0.09 times 0, and if you plug that into your calculator you get 0.9. Then if we go to corner point C, we'd want 0.06 times the 20 and 0.09 times the 5, and if you plug that into your calculator you get 1.65. And finally, if we use our last corner point, we'd want 0.06 times that 25 plus 0.09 times that 0, and that gives you 1.5. Now which one is your actual solution? Your solution is going to be the one that gives you the maximum income, because that's what we were looking for. So which of these i's over here is a maximum value? Well, if you rank these, 1.6 is biggest. So this is your maximum right here. So what is our solution? Our solution is that we are going to have a maximum income of 1.65 what? Remember what our units were? Remember how we defined our units? Our units were in thousands of dollars. So this would be $1.65 thousand, or in other words, if you move that decimal 3 spots to the right, $1,650 if we invest for X. Remember what this came from. X was 20 and Y is 5 right here. And X was your treasury bills. So we'd want to invest $20,000 in our treasury bills, and we'd want to invest 5,000 using those units of thousands in our corporate bonds. And that's our solution. Okay? So let's summarize this process that we just talked about. Here's the 4 steps that you want to go through. Number 1, write an expression for the quantity that you want to maximize, or sometimes these problems are looking for a minimum. So either maximize or minimize, and that is called your objective. So whatever it is you want to maximize or minimize, write out a formula for that, and that is your objective. Number 2, write out all the constraints that are listed in the system of linear inequalities and graph them and shade in that region. Step 3, find the corner points of that shaded region, and those are going to be your feasible points. Step 4, find out what the corresponding value of the objective function is at each corner point. And all you're going to do to figure that out is plug in the x and plug in the y into your objective function. The largest of these would be your maximum. If you were looking for a minimum, then the smallest of those would be your minimum. Okay? So let's try a very simplified example here. This time it's not really a word problem, it's just a set of equations. So it's most of the work is already done for you, the hard part anyway, in setting up all these systems. So what it is we want to do is minimize this expression. So this is what we call our constraint. And we have all of these, sorry, that's not your constraint, that's your objective, excuse me. So this is called your objective because that's what we want to minimize. And all of these down here are called your constraints, all those inequalities. So once you've labeled what your objective function is and what all your constraints are, what you're going to do next is you're going to graph all of these constraints in your system of linear inequalities. So let's start with the first one. Y less than or equal to 5. So here's 5, horizontal line, and less than or equal to 5 would be shading downwards. X equals to 6, that's a vertical line, and we want less than, so we're going to shade to the left. So far these would overlap down here. Okay? Then we want to graph x plus y equals to 2. If y is 0, x is 2. So we have an x-intercept at 2. And if x is 0, y is 2. So we have a y-intercept at 2. So we're talking about this line right here. And if I were to plug in the origin as my test point, 0 plus 0 would stay 0. Is 0 greater than or equal to 2? That's false. And the origin would be below the line, so that means we want to be shading above the line. So far, where do these 3 regions overlap? Above the line, to the left of the vertical, and below the horizontal. We're talking about this triangle right here. Okay, the next constraint, we want x greater than or equal to 0. Well, x equals to 0 would be the y-axis, and greater than it would be to the right. So now we're talking about this quadrilateral right here. And finally, y greater than or equal to 0, that's the horizontal line at 0, in other words, the x-axis, and greater than or equal to it would be up above. So now we're talking about this shaded region here. We're to the left of the y-axis, above the x-axis, above this slanted line, to the left of the vertical line, and below the horizontal line. So this is our feasible, these are all our feasible points. And the actual solutions are going to come from all of our corner points. So here, 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 and here. Let's call this A, B, C, D, and E. So let's list out the coordinates of each of our 5 corner points. So corner point A is right here, and notice that that is the y-intercept of this line x plus y equals to 2. So it has an x value of 0 and a y value of 2. Corner point B is also on the y-axis, so it has an x value of 0, but its y value is 5. Corner point C is when x is 6 and y is 5. Corner point D is when x is 6 but y is 0. And corner point E is the y-intercept of our line x plus y equals 2, the x-intercept of our line x plus y equals to 2, so that has an x value of 2 and a y value of 0. Alright, now to figure out which of these is going to be our actual solution, you go back to your objective function up here and you're plugging in the x and the y into that objective. So my formula for z is z equals 2x plus 3y. So z is going to be 2 times 0 plus 3 times 2, plugging in 0 for x and 2 for y. And that's going to give me 0 plus 6, or just 6. If I plug in the next point, point B, into z, I'm going to get 2 times 0 plus 3 times 5, which gives me 0 plus 15, or 15. If we plug in our third point, we want 2 times 6 plus 3 times 5. That's 12 plus 15, so that's 27. If we go to our fourth point, that's 2 times 6 plus 3 times 0, so that's 12 plus 0, or just 12. And our last corner point, 2 times 2 plus 3 times 0 gives me 4. Now, which one of these is our solution? Remember that we were looking for, in this problem, a minimum. So we want to be looking for the smallest z in this list. So right here is my minimum right here. So our solution is going to be x needs to be the 2 and y needs to be 0. And that will give you your minimum. If the problem had asked for the maximum, then that would be here, and x would need to be 6 and y would need to be 5. Okay, let's try one last example, another word problem. It's kind of intimidating when you first look at it. So let's read it through very carefully and we'll try to work through what we're dealing with. So here we have, at the end of every month, after filling orders for its regular customers, a coffee company has some pure Colombian coffee and some special blend coffee remaining. The practice of the company has been to package a mixture of the two coffees into 1-pound packages as follows: a low-grade mixture containing 4 ounces of Colombian coffee and 12 ounces of special blend coffee, and a high-grade mixture containing 8 ounces of Colombian and 8 ounces of special blend. A profit of 30 cents per package is made on the low-grade mixture, whereas a profit of 40 cents per package is made on the high-grade mixture. This month, 120 pounds of special blend coffee and 100-pound Colombian coffee remain. How many packages of each mixture should be prepared to maximize profit? Assume that all packages prepared can be sold. We're missing a C right there. All right, so here's my situation. There's a lot of information going on here. So let's sort of sort through it all and see what we can figure out. First of all, what is the unknown and what is it that we're trying to do here? Look at this last question here. How many packages of each mixture should be prepared to maximize profit? So how many packages means we're looking for how many packages of the low-grade mixture and how many packages of the high-grade mixture. So let's let X be the number of packages of the low-grade mix, and let's let Y be the number of packages of the high-grade mix. So those are my variables, and for all the ones that I'm going to ask you to do, you're only going to have two variables, because if you have more than two variables, it gets too complicated for us to do. So we're just going to have two unknowns, x and y here. What is our objective in this problem? What is it we're trying to maximize or minimize? We're trying to maximize profit. So to come up with our objective function, we're trying to come up with a profit function. So how do you calculate profit here? Well, it's going to be the number of packages of this low-grade mix times the price that we earn from selling them, plus the number of packages of our high-grade mix times the price that we earn from selling them. And it says up here that we get a profit of 30 cents per package on the low-grade mixture. So that would be 0.3 times however many packages we sell, which is our x. And then we earn a profit of 40 cents per package on the high-grade mixture. So 0.4 times the number of high-grade mixes we sell, which is our y. So here's our profit function right here. All right, now for the tougher part, the constraints. So the first two are going to be sort of those implied constraints that aren't necessarily spelled out in the problem, but they do exist. Since we're talking about x and y being the number of packages of these mixes, they can't be negative. You can't have or sell a negative amount of packages. So this x must be greater than or equal to 0, and this y must also be greater than or equal to 0. Now the other two constraints that we're going to have come from the fact that we have 120 pounds of special blend coffee available to put into these mixes, and 100 pounds of Colombian coffee remain to put into our mixes. And how do we create these mixes? Well, we have, for the low-grade mix, 4 ounces of Colombian coffee and 12 ounces of special blend. And then for the high-grade mixture, we use 8 ounces of Colombian coffee and 8 ounces of our special blend. So let's talk about our 120 pounds of special blend coffee that's remaining and our 100 pounds of Colombian coffee remaining. And let's think about what we get to do with that. So if we have 120 pounds of our special blend, how is that going to be divvied up between these two different mixes? Well, we have to use 12 ounces of it in our high-grade mixture, our low-grade mixture, and we use 8 ounces of it in our high-grade mixture. So 12 ounces in the low grade. So 12 ounces in our low grade would be 12 times x plus 8 ounces in our high-grade mixture would be 8 times y. So this is the amount of coffee of the special blend type of coffee that's going to be used between our two mixes. We'll use 12 ounces of it in X packages of the low-grade mixture and 8 ounces per Y number of packages in the high-grade mixture. And that total amount of coffee can't exceed this 120 pounds. Now a little bit of units going on here that's going to cause us some confusion. This 12 and this 8 are ounces and 120 is pounds. So we have to do a little bit of unit conversion here. 120 pounds, we need to convert that to ounces. If I'm using ounces on the left side, which are the 12 and the 8, I need to use ounces on the right side. So how many pounds in ounces? Well, there's 16 ounces in 1 pound, and 120 times 16 is 1,920 ounces. So we have 1,920 ounces of special blend coffee available to use. 12 ounces are devoted to 12 ounces per package are devoted to the low-grade mixture, and 8 ounces per package are devoted to the high-grade mixture. So that's kind of our constraint on the special blend. Then we're going to do something very similar for the 100 pounds of Colombian coffee that we have available. Again, we need to do a little bit of unit conversion here. If we have 100 pounds of Colombian coffee, 1 pound is 16 ounces. That means we have 1,600 ounces available to use. So we need to use 1,600 ounces. And how are we using that Colombian coffee? Well, 4 ounces of it go to the low grade mixture. So 4 ounces times the number of low grade mixture packages that we create, plus 8 ounces per number of packages in the high grade mixture. So those are a little bit tricky to figure out, but this one is basically how we're devoting or splitting up that special blend coffee between our two package types, and this is how we're splitting up that Colombian coffee between our two package types. So now we have all of our constraints. We're ready to go ahead and make a graph. So we're going to draw a picture here for my constraints, and already I know that x greater than or equal to 0, that's to the right of that vertical line, and y equals to 0 is up above that horizontal line. So we're talking in this first quadrant so far. That's what these first two constraints require. So now we go to our second two constraints, and we need to figure out how to graph these. So if we look at the first one here, let me just do a little bit of scratch work. If we take this first equation, 12x plus 8y equals to 1920, we're just going to find a couple of intercepts in order to graph it. So we're going to let x be 0 and we're going to let y be 0. So if I let x be 0, this goes to 0, and we're trying to figure out where 1920 divided by 8 is. So if we pull up our calculator and we do 1920 divided by 8, we get 240. And then if we let y be 0, we need 1920 divided by 12. $160. So those are my two intercepts. Let's go ahead and figure out what the graph of that's going to look like. So 240 somewhere up here, and 160 somewhere over here. So this is that equation right there. And if we were to use the origin as our test point, this whole left side would be 0, and 0 is less than or equal to 1920, so we're talking about shading below that line. Okay, let's go ahead and do the second equation here. 4x plus 8y is equal to 1600. Let's get a couple of intercepts for that. If x is 0, 1600 divided by 8 is 200, and if y is 0, 1600 divided by 4 is 400. So my intercepts are going to be 200 on the y, so a little bit lower, and 400 for the x, which is way over here. So graphing that, it's going to look something like this. And that's that equation. So if we were to plug in the origin into that as well, 0 is less than or equal to 1600, so we would want to shade below that line. So where do all four of these regions intersect? Remember, the first two require us to be in quadrant 1, so we're restricted on the left by that y-axis and on the right, or below by the x-axis. We want to be below this line, and we want to be to the left of this line. So we're talking about this region right here, that sort of quadrilateral shape. And then we have 4 corner points. So we have A, B, C, and D. So let's find out what all of these corner points are. A is obviously the origin. B is this y-intercept, so x is 0 and y is 200. Let's skip to D for a moment because that one's a little bit easy to see as well. That's the x-intercept. 160 for x and 0 for y. C is the tricky one because it's not obvious what x or y is. So what you have to do to figure out what C is notice where it's occurring. It's the intersection of these two lines. So C is the intersection of our two equations, 12x plus 8y equals 1920, and 4x plus 8y equals 1600. So how could I find the intersection of these two curves? Well, this is a 2 by 2 system of equations. That's what we're really trying to solve when you're asking for an intersection point. So you can solve this any way you like. You could use substitution. I like it to do with elimination because the x's and the y's are all lined up. The only thing I'm missing here are negatives in front of that 8, and then these would be opposites and I could cancel out right away. So let's multiply everything through by a negative. 12 minus 4 gives me 8x. These cancel out, and 1920 minus 1600 is going to give me 320. And if I divide by 8, that gives me 40. So the x value of this intersection point is 40. Now to find the y value, just take that 40 and plug it back into any of these two equations. So 40 is an x, so 4 times x would be 4 times 40, plus 8y equals 1600. So we get 160 plus 8y equals 1600. Subtract 160 to the other side. So this is 1440. Let me just write it a little bit neater here so we can see. So 1600 minus 160 is 1440. If you divide both sides by 8, you end up getting 180. So the y coordinate of this intersection point is 180. So that was a tricky one to find because we had to do a little bit of solving of this system. Alright, now that we have found our 4 corner points, all we need to do now is plug them back in to our profit function up here. So we're going to be plugging them in into p equals 0.3x plus 0.4y. So this profit p would be 0.3 times 0 plus 0.4 times 0, which is obviously 0. Then for the second corner point, 0.3 times 0 plus 0.4 times 200. And if you plug that in, you get 80. And this is profit, so I'm going to write $80 there. For the third point here, it would be 0.3 times 40 plus 0.4 times 180, and if you plug that into your calculator, you get 84. And then for the last point, if we plug in 160 for x and 0 for y, we get 48. And we're looking for maximum profit. So which of these profit numbers is biggest? Right here. So this is our solution. So we need x to be 40 and y to be 180. And remember what these represented. So 40, or x here, was our packages of our low-grade mix. That was how we defined it up here. So we need 40 packages of the low-grade mix, and we need 180 packages of the high-grade mix. That's how many we need to prepare and sell in order to maximize our profit. Okay? Alright, that concludes our lecture on linear programming. Good luck!